Yes, good morning. So here we will revise the topics what we have learned in the last few classes. Instruction code is, we learned that it is a set of bits, right? Group of bits that instruct the computer to perform a certain operation. The operation may include sequence of micro operations. And the main part of the instruction code is the operation code, because this tells the computer what the operation is to be performed. Okay, what is the operation that need to be performed is instructed by this operation code. And the address field specifies the address of the operand. Okay, address of the data. The data may be stored in the registers or it may be in the memory. Okay, the operation what is specified in opcode need to be done on the data. So we need to know the location of the data, where it is stored. Okay, so that location we will have in the address field of the instruction code. And this specifies the bit 15, okay, that is represented as I. The value of I may be 0 or 1. Okay, that if it is 0, that means the address here, okay, used in the address field is the direct address. And when the value of I is 1, it means the address is indirect address. So let's see what is direct and indirect address. Direct addresses, you see this example here. Okay, here we have the instruction at location 22. Okay, in memory, this is a memory that stores the instructions and data. Okay, we learned that memory is divided into two parts, right? If you take the memory, the stored program concept, where the data and the instructions are stored in the same memory. Okay, so it is divided into two parts, and in one, here this is instruction part and here is the operand. Okay, operand gets stored in this location and instructions get stored in this location. Generally, the instructions in a program get stored in consecutive memory locations. So here, let's say that at location 22, okay, we have this instruction. Okay, what is I here? The 15th bit is 0. That means it is direct address. Okay, and the operation says add. So the operation given here is, the opcode is add. And the address is 457. And we know that it is direct address because the value of I is 0 here. Okay, for this direct address, the address in the address field, okay, the number given here in the address field is the address, directly the address of the operand. So if you find this location 457, okay, where is 457 in memory? This one. Okay, at this location, we can locate the operand directly. Okay, that is why it is called direct address. Directly at the location specified in the instruction code, okay, we will find the operand. And indirect address. Indirect addresses, here you see this location at location 35, we have this instruction code, okay, where the operation is add, and the address mode, okay, I is 1 here. So it says that the instruction, the address here is not direct address, it is indirect. Okay, so what is indirect address? The address field will have the location where the effective address of the operand is stored. Okay, so where the operand is stored at location 1350. Okay, and this instruction will not have the direct address 1350. Okay, now this 1350 is stored at location 300. So the instruction will have this address. What is this 300? It is the location where the address of the operand is stored. Correct? 300 is the location where the address of the operand is stored. So this type of addressing is called indirect addressing. Okay, what is effective address? Effective address is the direct address of the operand. In this case, it is 457. And in this case, 1350 is the direct address. Okay, and the indirect address is 300. Okay, because it is at 300, we will not find the operand. We'll find only the address of the operand. And once the, finally, once the operand is located, okay, in the memory through direct address or indirect address, once the operand is located, it is the operation given in the operation code, okay, it will be performed with the content of the accumulator. Okay, whatever the operation is given in the instruction will be done with the content of the accumulator. Accumulator is a processor register, okay, 16-bit register that stores the data. Okay, so when the operand from the memory is found, okay, in this case the operand is stored in memory. Okay, and then it has to be fetched before processing. It need to be moved to the register DR, right? The operand will be moved to register DR. This is the data register. So finally, the operation given in the instruction code will be performed on the data in DR and the data in the accumulator, and the result gets stored in the accumulator. And we learned the 3 different types of instruction format, right? Instruction code format. This is the general format. Okay, here the address field specifies the address. This address may be the location of data in memory, or it may be the location of data in register. Okay, and here the 3 specific formats are, okay, the first format is this here, memory reference instruction uses this format. Okay, this is the first one. And the address for memory reference instruction means the data is in memory. Okay, so the address need to specify the location of data in memory. Okay, this address field, otherwise opcode is the operations that need to be performed. And the address field specifies the address of operand in memory, and I is the bit that says if the address used is direct or indirect address. And the second type of instruction code format is here, the 3 bits of opcode will be 111. Okay, always it is 111. Here, if you see the first format, the opcode is 3 bits. The number of bits used for this storing operation code. Here, if you see, it is a 16-bit. The instruction code has totally 16 bits. And out of 16, 12 bits are used for address. Okay, specifying the address in the memory. Why 12 bits? Because the memory is of size 4096. Okay, to specify the memory words of this particular memory, we need 12 bits. Okay, because 2 power 12 is 4096. This is what decides the number of bits in the instruction code for specifying the address. And how we find the number of bits, how we determine the number of bits used for operation code. That depends on the number of operations the computer performs. Okay, if the computer can perform 8 operations, okay, we need 2 power 3 is 8. Okay, so we need 3 bits to specify the operation. The instruction code, we need 3 bits, okay, to specify the operations or to define the operations of the computer that has 8 operations. So here 12 bits are used for address, and the 3 bits are used for operation code, and the last 1 bit is used for, because it is a single bit, the value will be 0 or 1. It is the 15th bit. And register reference instruction, we don't need to have a memory reference, because the operations will be performed on the data in the registers. Okay, there is no memory reference needed. So here in the address part, we will not have the memory address. Okay, and here the opcode will always be 111 for register reference instructions. Okay, to identify these instructions, we have these formats are differentiated like this. Here opcode are 3 bits. The 3 bits starts from 000 to means 8 different operations. So it is 111, correct? Okay, but this 111 denotes the register reference or memory input output instructions. Okay, so we consider for memory reference instructions, we consider bit 000, okay, to 110. Okay, that is 0 to 6. There's 7 operations. And when the 8th operation, when it is 111, the opcode is 111, it will be either register reference or input output instruction. Okay, so here this we are talking about register reference instructions, right? Here, the opcode will always be 111. And even for input-output instruction, it is 111. To differentiate this, we need to check the 15th bit. If you see in register reference instruction, the 15th bit is 0, whereas for input-output instruction, the 15th bit is 1. And the other 12 bits, the remaining 12 bits in register reference and IO instructions, okay, there is no memory reference needed. So the operation, okay, that is need to be performed will be specified in these 12 bits, register operation and IO operation in IO instructions. And we also learned about the instructions available in basic computer, all right? It is, as we have 3 formats. These are 3 categories of instructions. Here we have memory reference instructions. And these set of instructions are register reference instructions. And these set of instructions are IO instructions. Okay? And these are all the instructions that are performed on the data in the memory. Okay, if you see and memory word to the content of accumulator. Okay, so it performs the logical operation and on the data in the memory that is that can be located by the address. Okay, that is given in the address field of the instruction code. Okay, so for the memory word and AC, the content of AC, and add. Okay, it is to perform add, and this is to load content, load accumulator from memory. The memory word is taken and it is loaded into accumulator. Okay, so here all these instructions, if you see, we need the memory reference. Okay, so these are all memory reference instructions. And the second set of instructions are register reference. The operations are performed only on the data in the register. It is clear accumulator and clear the register E. It is a carry bit, okay? And complement accumulator. We don't need any other means operand, okay? On a single operand that is stored in the accumulator, it is performed. We have learned in detail, right? The micro operations, still we will discuss here later. And these set of IO instructions, these instructions are useful for the computer to communicate with the user through the input and output devices. Okay, so input INP is the instruction that takes the input character and stores it to AC. Okay, get the input character from the input device, okay, and to AC. So the register that comes in between the input device and the AC is INPR, input register. Okay, and OUT is the instruction that output the character from AC. AC will have the result, right? After processing, AC will have the result. So it will be transmitted to the output terminal. Okay. So in between the accumulator and the output terminal, we have OUTR. So the content will be transferred to OUTR and then later transmitted to the output terminal. This way, okay, we have these categories of instruction. These are the instructions in the basic computer. And we say that the instruction set in the computer is complete if it includes the instructions from all these categories. Okay, we need to have arithmetic, logical, and shift instructions, okay, to perform the basic operations. For performing the basic operations, we need the instructions from the category of arithmetic, logical, and shift instructions, and instructions for moving information to and from memory and processor registers. The data that is stored in the memory need to be transmitted before we will not perform the operations on the data in the memory. When it resides in memory, the operation cannot be performed. It has to be moved to the processor register, right? Moved to the processor for performing any operation. So there need to be instructions for moving the information from memory to processor and from processor to memory back. And we also need program control instructions. Okay, the sequential flow, normally the instructions are executed in sequence. And we need to have instructions that also sometimes take the control to the desired location, okay, for executing a different set of instructions, a procedure or function, or to skip a particular instruction. Okay, so we need program control instruction that controls the flow of execution. And we need input-output instructions. The input-output instructions are the instructions for the computer to communicate to the user through input and output device. So when the computer instructions include instruction from all these categories, we say that it is complete. So here in this instruction set, if you see, we have logical, this is AND is logical operation, and add is arithmetic operation, and load is transfer, right? Register transfer operation that moves the content of content between accumulate means register and memory, and even store. This is the transfer, register and memory transfer operation. BUN, it is the control unconditionally branching to another location, and BSA is also, okay, it alter the sequence, okay, by moving to another location, by branching to another location, and it also saves the return address, okay. And IS is it increment and skip if 0, and all these clear the accumulator, performed on registers, these all, okay. And we have also input output instructions, INP to take input, and OUT to print output, and skip on input flag, okay, checking the status of the input flag, skipping the instructions, okay. So when these when it includes all these categories, the instruction set is said to be complete. And we learned about instruction cycle, right? For every instruction in a program is a group of instruction, okay, group of instructions. So for every instruction, the same set of process need to be repeated for for its execution, correct? Same set of process need to be repeated for the execution of each and every instruction in the program. So this set of process, okay, we call instruction cycle. It includes fetch an instruction from memory. The first process is we need to fetch the instruction from memory, and we store it in register IR. For the execution of a particular instruction, it need to be taken from memory and moved to the instruction register, and then decode the instruction. So now you will have the instruction code, the coded format of instruction in the register. Now it need to be decoded, correct? For the computer to understand what is the operation to be performed. So the instruction need to be decoded, where the operand is located. All this need to be identified. For this, we decode the instruction. And after decoding, when the operation is known, read the effective address from memory if the instruction has an indirect address. If it has direct address, the address itself, during decode phase only, we will get the address. Okay, when the address is moved to the address register, in the address register, we will have the direct address, means the effective address. But in case of indirect address, we need to find the effective address of the operand. So that is the third phase. And the fourth phase is once all these are known, we know what is the operation need to be performed, and we have found the address. We know the address of the operands, effective address of the operands, okay, and then execution of the instruction can be done. Okay, so these are the 4 processes that need to be repeated for each and every instruction in the program. Okay, and it repeats for each instruction, so we call it as instruction cycle. And we have learned the different steps. Okay, here is the flowchart that describes this instruction cycle, that describes the micro operations performed. Okay, what is the first phase of the instruction cycle? It is fetch. Okay, for fetching an instruction, what we need to do, we need to take the instruction from the memory. We have the instructions stored in memory. Okay, this is our, let's say this is our first instruction, and this is the second instruction. And to execute this instruction, let me name it as I1 now. Okay, instruction 1. to execute this instruction, this need to be moved to register IR. This is what is fetching the instruction. Okay. So how we move this to IR? We need to know where this particular instruction code I1 is stored in memory, right? To find the location, we see what is PC, what is there in PC. PC is the register. It's a program counter. Okay. It will have the address of the instruction that need to be executed next. Okay. So if I check the, when we check the PC program counter, okay, it points to 1 because this is the instruction that need to be executed. Okay, so we take the address there in PC. So the content of this address need to be moved to AR and then locate the instruction, okay, in memory at this particular location. Okay, so these two instructions, if you see, okay, this is what is given here. Move PC to AR and at the memory address, okay, memory word at location AR is moved to instruction register IR. Okay, so once moved, now IR will have the instruction code. And then immediately PC need to be incremented because after taking this instruction, now this becomes the current instruction, correct? And PC need to point to the next instruction. PC will be incremented. Okay, so it will have this address too. So this is fetch. And the second phase of the instruction cycle is decode phase. Okay, so we need to decode. The components of instruction code are the operation code, and we have the address. We also have the 15th bit that says if it is indirect or direct address. So all these need to be found. And so we take the 12th to 14th bit of instruction code and move it in. We find what is the operation. Okay, we decode that and move 0 to 11. 0 to 11 is the address, right? Okay, move the 0 to 11th bit of instruction register into AR because that says the address where the operand is located. Okay, operand on which the operation is to be performed is located. And move the 15th bit to I. Okay, so this is decode phase. Okay, we learned this, how the opcode is decoded, correct? Okay, the coded opcode is given to the decoder. The 3 bits are given as input to the decoder and it decodes that and gives us from D0 to D7, correct? It specifies which particular operation is to be performed. Same way, okay, these operations need to be performed at a particular timing, right? So this timing signals are generated by the sequence counter. Okay, sequence counter, it's a counter, it starts counting from 0, okay, and generates the timing signals. Okay, it gets incremented every time by 1 and start generating the signal, timing signal T0 to T15, and it is decoded, whatever it is, the output of sequence counter is decoded by the decoder, and you get the timing signals from T0 to T15. And to clear the sequence counter, once one particular instruction is executed, it has to start from T0 again. Okay, so it need to be cleared. Okay, so fetching the instruction is done at time T1, T0 and T1. And at time T2, we have the decode phase. Okay, it decodes the instruction in the 12 to 14 bit of instruction code. Okay, the opcode and 0 to 11 bits. Okay, the address is moved to address register and the 15th bit is moved to register I. And now we check, after decoding, we check the output of the decoder. Okay, that is D7. When D7 is 111, means it is not memory reference instruction. Okay, So other cases, it is considered as 0, and when it is 1, 1, 1, it is 1. Okay, the decode D7 is 1. So we check D7. If it is 1, means it is register reference or IO instruction. When the decoder output D7 is 0, it is memory reference instruction. Okay, now we need to, the next phases. We finished fetch phase and decode phase. And now the next phase is to find the effective address. Okay, so we see if for memory reference instructions, we see if the address is direct or indirect by checking the ith bit. If I is 0, it is direct address. Okay, we don't have to do anything because already we have the direct address in address register. So in case of indirect address, okay, if I is 1, we need to move the address, okay, that is specified by this particular location. Okay, what is an AR? We need to move that to AR. Now this is the effective address of the operand. Okay, so at time T3 in memory reference instruction, at time T3, third phase is completed. Okay, finding the effective address in case if the address is indirect address. And after this, the sequence counter is incremented. Okay, it generates T4. At time T4, the execution of memory reference instruction is done. So this is one instruction, the set of operations performed for one particular instruction, fetching, decoding, and then finding the effective address and executing the instruction. Now the sequence counter need to be set to 0 because it has to again start from T0 for the next instruction. Okay, so it is set to 0, cleared. And here when D7 is 1, we check the ith bit because we need to know whether if it is register reference or IO instruction. If it is registered, if it is 1, execute IO instruction and set SC is 0. And if it is 0, if I is 0, execute register reference instruction. Yeah, this is a flowchart for instruction cycle, including the interrupt cycle. Okay, if you see, we have here the interrupt cycle and here is the instruction cycle. Okay, instruction cycle is what we have seen here, the same thing. And R is checked, right? For during execution of every instruction, R is checked, the interrupt flip-flop. So we also check before executing the instruction, R is checked. If R is 0, this instruction cycle is done. Or when it is 1, it has to go through this interrupt cycle. Okay, and you know the sequence of operations that are involved in the interrupt cycle. The content of PC, the address need to be, means the return address. Okay, what is there in PC need to be moved to 0th location in memory, and PC need to be incremented. PC need to be moved to location 1, and the execution of the interrupt service routine, okay, is done. So once it is serviced, IEN is set to 0. Interrupt enable flip-flop is set to 0. And R is set to 0 and SC. Okay, once the instruction, all the instructions are executed, it is set to 0. And here, this table shows the control functions and micro operations for the entire computer. Okay, it is the summary of all the what we have learned in this chapter. Okay, you know what is fetching. Okay, fetching the instruction from memory. So we need to have the address. Address that is there in PC is moved to AR. At that particular location, the instruction is moved to IR. And PC is incremented for the next instruction. And what is decoding? Decoding means the coded information we have in the opcode instruction code. Okay, so opcode part of the instruction code need to be decoded. It is given sent to the decoder, and it is what is the operation? Okay, that has to be performed is found. Finding the meaning of the instruction code. Okay, and when you and these micro operations, these are the micro operations that are performed. And the control conditions. Okay, in this table we have all the control conditions and all the micro operations for each and every operation. the fetch phase of the instruction cycle. Okay, the control condition is R dash. We have seen this in this flow chart. Okay, R need to be 0 for instruction cycle. For interrupt cycle, R is 1. Okay, the interrupt flip-flop is set to 1. Then interrupt cycle is executed. So here R should be 0. Okay, so we write R dash, and at time T0 and T1, fetch is done. Okay, this is fetch operations. And the second phase is decode, correct? For decoding, it has to be done at, all these the operations performed in instruction cycle, okay, for execution of the instructions. So here R is 0, okay, R dash, at time T2, decoding is done. If it is indirect address, okay, here this is the special case. If it is a direct address, you will have the effective address in AR here at time T2, okay, in the second phase. If it is indirect address, in the third phase, okay, here I need to be 1 in the instruction code. D7 dash, D7 is 0 for memory reference instructions, and I is 1, and time T3. At time T3, we move the memory word at location AR into AR. This is the effective address of the operand. Okay, so this is the third phase, finding the effective address. And the fourth phase is here, okay, execution. It starts from here. Memory, in case of memory reference instruction, okay, we know all these operations, and performing and. What are the micro operations? What is the control condition? What is the control condition for and? It is D0, right? The decoder output D0. When it is opcode is 000, the decoder output D0 will be active. Okay, so D0, and at time T4, the first micro operation is performed. Now we know the address. Already we have the address in AR. So fetching the operand from memory. The memory word at this location is moved to DR, because operation, for performing the operation, we need to have the operand in DR. Okay, and the next step is, okay, when decoder output is D0, means the same operation. At time T5, the next micro operation is performing AND. Okay, you can, this is AND. Performing AND on the content of AC and DR, and store the result in AC. So execution of this operation is done. If in case the opcode is 000 and decoder output is D0. And if it is 001, so the decoder output will be D1 here. So this case, the operation performed is add. Okay, decoder output is D1 at time T4, the first micro operation. Same, fetching the operand from memory and taking in DR. And the second micro operation at time T5, adding it to the content of AC and storing the result in AC. And we will also have a carry out during addition, that is moved to flip-flop E. And when it is 0, 1, 0, the decoder output will be D2. Okay, so here if you see the control condition for the third operation, LDA, D2 at time T4, get the address, get the data from the memory and store it in DR. Okay, because it is to loading the content of memory, load the data into accumulator. Okay, LDA. So you need the data in DR and then move it to AC. The next micro operation at time T5, move this to AC accumulator. And next 0, 1, 1. And the decoder output will be D3. Okay, in this case, it is STA. It is STA means store the accumulator content into memory. So you have to move the content of accumulator into memory. Okay, so move, it is a single operation. Okay, we have only one micro operation to perform this STA. Okay, so we directly move the content of accumulator in the memory, okay, specified by this address. And when it is 100, it is D4. Okay, when it is D4, and at time T4, BUN, the operation performed is branch unconditionally. Okay, so we need to get the branching address, where to move, where to take the control to. That to be moved to PC. Okay, so the next instruction will be that particular instruction. And when it is 101, this is D5. And when it is D5, at time T4, BSA, branch and save return address. Okay, so return address is in PC, correct? That is the next instruction. So we save it in memory location at the given address and increment AR, okay, and store this into PC. That is the branching location, okay, because PC need to be pointing to the location to be moved. And IS is it is increment and skip F0. Okay, so when it is 110, decoder output D6 will be active in this case. When it is D6, the instruction for incrementing the data, okay, that is taken from memory, and then check if DR is 0, skip. Okay, skip the next instruction. This is performed. Okay, so all the control conditions with the micro operations for memory reference instructions. And same here, the control condition for register reference instructions. D7, what is the control condition for register reference instruction? D7 need to be 1 and I need to be 0. Okay, so it is I dash here, and at time execution is done at time T3. Even our input output instructions are done at time T3, but here I will be 1 for register reference, input output instructions. Okay, so that is written as R here. Okay, in short, we write it as R. And we also consider the ith bit. Okay, for the control condition, we include the ith bit that is set to 1. Okay, in the address field. Okay, so the first time it is B11 and next B10, B9, because it has 12 different operations. Okay, so 0 to 11. And in IO instructions, we have 6 different operations. So it is from B6 to B11. Okay, when the bit that is 1 in the address field. There is no address field here because there is no memory reference. The bits 0 to 11 in the instruction field, instruction code, specify the register operations and IO operation. Okay, in that, the bit 1, we discussed it earlier. Okay, and all the micro operations are given here, the control conditions and micro operations. This is for the normal execution. And during execution, the control also has to, the computer checks for interrupt, correct? Okay, when R is equal to 1, means there is interrupt. When R is set to 1, when there is, it is not fetch. Okay, the fetch phase is done at fetch phase of the normal instructions. Okay, it's done at T0 and T1. And this is decode phase, T2. Okay, so when it is not during fetch and decode. So T0 dash, T1 dash, and T2 dash. And this at time T3. Okay, at time T3, when IENS enabled, IENS check. If the value of IENS 1, and either input flag or output flag is set to 1. Okay, these conditions, when these conditions are true, R is set to 1. When R is 1, it has to go through, the computer has to go through the interrupt cycle, not the instruction cycle. It cannot execute these instructions. It has to stop the execution of other instructions, and it has to go to service the interrupt request. Okay, interrupt signal is sent from external or internal interruption. So when it finds R is 1, that is indicated by setting the value of R is 1. When R is 1, the control has to execute the interrupt cycle. It is stopping the current execution and moving to another routine, another procedure. Okay, so the return address need to be saved. That is stored in memory address 0. Okay, the return address is stored, and then PC is moved to location 1, and it executes the interrupt service routine and sets all these flags to 0. Okay, because once interrupt is serviced, it can be set to 0, and then R will also become 0. So this table in your book, page 162. Okay, just go through that and try to write all these instructions, micro operations and the control conditions on your own. Revise all the earlier topics and then try to write this table on your own. Okay, then you can make sure that you you have understood it clearly. If you have any doubts, you can ask me.